Part 2 of Lecture 8. So we will continue our task of finding a really simple feature and a really simple classifier to do real-time face detection. And the problem here is we have lots and lots of regions and not lots and lots of faces. So we want things to run really fast. So there are two parts to this problem. One is figuring out what kind of simple feature can we use that can be computed very efficiently, very fast. And the second is what kind of classifier do we use? So we probably want to use, because we have simple features, we want to use very simple classifiers. And remember, when we talk about decision trees, we talk about bagging and boosting to combine lots and lots of not so good simple classifiers into a good one. And we're actually going to use boosting here to combine them. And the good news is that as long as each one is like slightly better than randomly guessing, then it's okay. And then we combine them, then they will become a strong classifier. And so that's basically what we are trying to do here. So first thing, what kind of simple feature are we going to use? So to figure out the features, we may want to use some special properties of human faces. So we may want to use some domain knowledge about human faces. For example, the eye region is darker than the forehead and darker than the nose, and the mouth region is darker than the chin. So I think the description is not that clear. Let me show you an image of a human face. So for example, something like this. So the eye region, the eye region is darker. So if we use the pixel intensities in this region, subtracted by the pixel intensities in that region, in the forehead region, then for a human face, that value may be large, right? So similarly, if we use the intensity in this region plus this region minus this region, it may be large as well for a human face. So these features may be good features for representing a human face. And they seem like they are just like sum of pixel intensities and take the difference. And it looks like they are very easy to compute. And actually, they are called Haar features. And in general, Haar features are just rectangular region, the sum of their pixel intensities, and take the difference between multiple regions. And it's summarized here. They are just differences between sum of pixel intensities in rectangular regions. That's the very simple definition. And next, how are we going to compute it really fast? I mean, even faster than every time we sum up like lots and lots of pixels, right? So if you have a large image, if you want to sum up like this huge region, you still take some time. So we want this to be constant time computation. So the trick we're going to use is called the integral image. So as the name suggests, we're going to integrate this image. Sounds like fun, but it's just summing up stuff. Anyways, so the integral image value at this particular point is just the sum of all pixels that's to the left and up. So of course, if we want to do this for all the pixels, it seems we need a lot of computation, but of course we're going to do it recursively. So if we look at, for example, that value, so we want the integral image at that value, what we have is we have already computed the integral image at this value and also at this value and also at that one. So obviously we can combine them somehow, right? So we can use this to add this and also add this current pixel. Of course we need that, and we can subtract that region because it's double counted. So it's only 4 computations, actually only 3 operations, and we can compute basically the next integral image value. Instead of every time we need to sum up everything. So that makes computing the integral image very fast. And here the notation I'm using is the first I is integral and the second I is that particular image. So may not be a good notation, but I can think of a better notation for an image. So I'm going to start with this. And this is basically the formula that I just described. And we can use the same logic to compute the sum in any rectangular region, basically, for the Haar feature. Let's use a diagram again. So suppose we want to figure out the sum of pixel intensities in this region. Then note that we have the integral image value already. So we have the sum in this region, and we'll probably subtract it by the sum in this region. And then we don't have this small region. Let me change the color. We don't have this only, so we will subtract this again. So there is some kind of double counting. So we will add that region back. And that's basically what we are doing. It's described by this formula. So again, to calculate the sum of pixel intensities in any rectangular region, there are only 3 operations. So these Haar features are really, really fast to compute again. So now we have the features that look possibly reasonable, but they're very fast. So the next thing is how to deal with the classifier. So as I mentioned about ADA boosting, we were using decision trees at that time, and in particular, I mentioned the decision stumps, which are decision trees with only one split. They are like as simple as we can get. So we are going to build a decision stump on each one of the Haar features. So what we can do, for example, is we have lots and lots of face images. And for one particular Haar feature, for example, just that one, these are faces, and these are not faces. So these are y equals to 1 label images, and these are y equal to 0 images. What we can do is we can try different values of the split and maybe find the information gain that's the largest. And of course, we're not going to do that because that takes too long, right? So we are going to do something that's kind of is reasonable and actually works. It's basically I'm going to just sum up, take the average of all face images, take the average of their Haar features, that particular one, and also take the average of the non-faces, so these two values, and then we take the average of these two. So we just want the midpoint between the two average values. So it's definitely not clear why this works, and it seems reasonable. It's kind of intuitive. We could do that, but mathematically it's not clear why they're good. But well, like many of the computer vision algorithms you have seen, they work, and we don't know why, but that's basically what we're going to do here. So we basically use some kind of intuition to figure out what the split should be, and we use a very simple classifier. So this is as simple as it can get. And as I promised, we're going to combine them. So we're going to use adaptive boosting. So I'm not going to repeat the whole thing, but I'll briefly talk about it again. So what we're doing is we start with one weak classifiers, and for the next one, we focus on classifying the things that are classified incorrectly by the previous classifier, and we keep doing that. So the later ones will be focused on harder examples, basically. And then in that way, if we combine them, the combined classifier will be a stronger classifier. And here we will just call them T strong classifiers. And that is a sequential classifier with T weak classifiers. And what we're going to do one step further is we're going to create multiple of these. And it will be called a cascaded classifier. And let me actually explain what's happening here. So what we want to do, as I mentioned before, in an image, there are only like a few faces, but lots and lots of regions are non-faces. So we want to get rid of those very quickly. So instead of training one single ADA boost strong classifier with like millions and millions of weak classifiers that is really accurate, what we'll do here, if we do that, the first region is very difficult. It takes a long time to actually classify this, and the second region takes a long time to classify that as well. So instead of doing that, for each region is kind of slow, let's train a strong classifier that is like not that strong with a small value t. So we use those not so strong classifiers to just get rid of those like obvious non-face regions. And then in the remaining regions of the image, we can use something that's like slightly stronger strong classifier, basically strong classifiers with larger t-value. And then we can get rid of some of those non-face regions, and then we just keep doing this. So why is this helpful? It's because, again, it's specific for face detection that lots and lots of regions are not faces. So we want to get rid of them quickly using a classifier that's really, really fast. And that's the basic idea behind cascading classifiers. And I think it's not clear without a numerical example, so I want to talk about one. And the example will be at the beginning, we just use like 1 week classifier, and hopefully we can achieve 100 detection rate. And what I mean by that is it does not reject anything that's actually a face, but it can not reject things that are not faces. So it's really good at rejecting non-faces, but it's not good at figuring out which maybe face ones are actually faces. And then we can continue with a better strong classifiers, and they need to do the same thing. By the way, they cannot reject actual faces, but they need to be better and better at rejecting non-faces. So if we do this one next, and then we get a even stronger classifier, again with the same 100% detection rate and even smaller false positive rate, but basically rejecting non-faces, then when we cascade them, when we combine them in this sequential way, then the detection rate will still be 100% because like every step is 100%, but the false positive rate is multiplicative. So suppose we actually have these, then we actually have a 2% false positive rate at the end. So it's actually very small with only a few classifiers, and it will be very fast because only a few non-faces will get through the first pass, right? So you only have a small number of regions to check for the second pass, and then you have an even smaller set of regions to check for this very large strong classifier. So it takes less time to classify the regions that are non-faces with this very strong classifier. So that's the idea here. So combining what we said so far, this algorithm is called Viola-Jones. And of course, like all the other computer vision algorithms, we are going to use some kind of very specific parameters that we don't know where they came from. Well, they came from experiments on actual images, and it seems like 24 by 24 region works well, and it seems a factor of 1.25 works well. So these parameters are not that important. They are just calibrated so that it works for this special task on real-life images. So I will not spend time on talking about these, but one thing I do want to talk about is the stride and this multiple detection problem. So let's load another image. The frozen one maybe is good. So what we're going to do is we're going to have those 24 by 24 regions, and we're going to, of course, we're going to scale this at multiple scales in order to get like faces at multiple scales. But the idea is we're going to use just sliding window and move with a stride 1. So remember, when we talk about convolution, we talk about stride. So the 24 by 24 region, we just move to the right by 1 pixel each time. So there are lots and lots of windows, but since, as I said, the classifiers are very fast, so we can move around them really, really quickly, especially in the first few passes with very few weak classifiers, meaning T-strong classifiers with small t. And so these paths will be very fast. And that's the stride part. And the other part is, suppose we want to classify, we want to figure out this region. If you think about a nearby region, that would also be a face. And if you figure out another nearby region, that would also be a face. Also, if you figure out the one in a smaller scale, that also looks like a face. So in those cases, we need to combine the overlapping regions that we classify as faces into one, and that will be the last step at the end. So here in this region, there are lots and lots of 24 by 24 regions at different scales that are classified as faces. We just keep one that's maybe say the largest that contains all of them. And if you look at this, actually there is it's not clear. Let me erase this. This is something that's not really a face, but maybe the pixel values resemble a face, and there is this region that's should be a face, but maybe it's just not human enough, but should be detected as a face.